This video will review combining random variables from Unit 4. First, let's refresh on shifting and scaling distributions. This is from way back in Unit 1. If we have a data set and we add or subtract a constant to all the numbers in that data set, that's going to change measures of center and location, things like the mean, median, quartiles, minimum, maximum, etc. However, it won't change measures of spread. Standard deviation, range, IQR are all going to be the same if we add the same number to every value in the data set. If, on the other hand, we multiply or divide a constant to all the values in the data set, that's going to change everything. Changes measures of center, location, and spread. As a last note, remember that variance is the square of the standard deviation. So if we multiply by a constant, it changes the standard deviation by that amount, but it'll change the variance by the square of that amount. Now, when it comes to combining two random variables, if we're talking about the means, we can just add or subtract them logically and do a simple calculation. However, we can't do that for standard deviations. We're not allowed to just add them or subtract them. Instead, we add their variances. Variance being the standard deviation squared, and then we square root the sum of those variances. We're always going to add the variances, even if we're subtracting random variables. As an example, here we have two random variables, x and y, and each has their own mean and standard deviation. When we're finding the mean and standard deviation of x plus y, the mean is logical. We just add these two means together. X plus y is going to have an average value of 150. Standard deviation, we are not allowed to do this and just add the 8 and the 6 together. That's not allowed. Instead, what we have to do is add the variances of both of these individual random variables. So we find the variance of x, which is 8 squared, add the variance of y, 6 squared. That totals 100, and then we square root the sum of those variances to get the standard deviation of the sum of x and y. If we change this problem to a minus, now we're finding x minus y. Mean, we just subtract them. They would have an average result of negative 50. And standard deviation is found the same way. It doesn't matter that this is a minus sign. Our uncertainty in this average still compounds with every additional random variable that we add on. So we always add variances regardless of what sign we're doing with the means. So here's an example of a random variable word problem. We have two stores selling watermelons. The first store has watermelons that average 22 pounds with a standard deviation of 2.5 pounds. The second store has smaller watermelons which average 18 pounds and a standard deviation of 2 pounds. Part A, what's the mean difference in weights of these melons? We can just subtract these two numbers logically. On average, they would have a difference of 4 pounds. Standard deviation of the difference. Now we're working with these numbers here, and we can't just subtract them. We're not going to subtract them at all, actually, because we always add variances. Square both of those numbers, add them together. We get radical 10.25, which is 3.2 pounds. Part C, if a normal model can be used to describe the difference in weights, what's the probability that the melon that we got at the first store is heavier? This is a z-score problem, mentions a normal model, and up here we found the mean and the standard deviation, and that's going to be the parameter values of our normal model. So important thing to note is that this distribution is about the differences in the weights of these watermelons. So we would expect them to have a difference of 4 pounds. A difference of 0 would be where these two watermelons weigh the same amount. So that's the cutoff we're interested in, and we have to figure out which side of the curve to shade. And this really becomes a logic problem. So if we come back up here, in the first store, the watermelons average 22 pounds. That's larger than what they average in the second store, 18 pounds. So in other words, it's more likely to have the watermelon on the first store weigh more than the one at the second store. So since it's more likely, we want to shade the right side. Okay, if it was less likely, if this number was smaller than 18, we would want to shade over here. So we want a z-score for that cutoff of 0 with this mean, this standard deviation. We get a z-score of negative 1.25, and then we jump over to normal CDF to get that probability. There's an 89.44% chance that the watermelon at the first store will be heavier. This next example is a full FRQ from the 2013 AP test, and like most FRQs, they like to throw something at you that makes you think outside the box a bit. So here it's talking about a carton of 12 eggs. It includes one randomly selected cardboard container and 12 randomly selected eggs. It tells us that the mean of this total container with the eggs is 840 grams with a standard deviation of 7.9 grams. Part A, just a z-score problem. What's the probability that a randomly selected full carton of eggs will weigh more than 850 grams? This one's pretty straightforward. Find the probability that we end up at 850 or to the right of that, 850 or larger. We get a z-score of 1.27. If you write this, which you don't have to, make sure you label the mean and standard deviation of the populations using mu and sigma. Probability that the carton weighs over 850 grams is 10.2%, or 0.1020. Here's the actual rubric for this. We want to note or indicate the use of a normal distribution, clearly identifying parameter values. We meet that criteria by writing this. Okay, we also would meet it if we wrote the actual equation with the variables over here, which we typically don't. That's why we always write this when we draw a normal distribution. Uses the correct boundary value. Okay, we indicate that over here when we draw our curve. That's why we always want to sketch our curve. Reports the correct probability consistent with what you wrote up here. Okay, and that's this part right here. If you have all three, it's an E. If you have 2 out of the 3, it's a P. Just one extra note, I know some of you guys have figured out you can change this mean and standard deviation in your calculator, and it's just going to give you this value. Make sure you write these 2 symbols here. That's what is getting you credit for that point there. I'd prefer you just to have this whole sketch drawn out and math work, because not every rubric matches this one. In part B, it tells us that the weights of these empty cardboard containers is 20 grams with a standard deviation of 1.7 grams. It's followed by a whole bunch of information saying that all of these things are independent of one another. There's 12 eggs in the carton. They're all independent. The weight of the carton is also independent. We don't know what the eggs weigh. We're going to let X represent the weight of a single egg. And then in the 2 sections for part B, it's saying what's the mean of X, what's the standard deviation of X. So to summarize all the information here, we know that the total container from the original stem of the problem has a mean of 840, standard deviation of 7.9. We know that an empty container has a mean of 20, standard deviation of 1.7 grams. And we're looking for what are the mean and standard deviation of X, where X is the weight of a single egg. There's 12 eggs in a container. Section 1 is pretty straightforward. It's just an algebra problem. We know that the total container is going to include 12 eggs plus the empty container. We can plug in everything we know about the problem. So we know that the total container is 840 grams. We know the empty container is 20 grams. We don't know what these 12 eggs equal. We know a single egg, or we're representing the weight of a single egg with X. That's our equation. Subtract 20, divide by 12. Each egg weighs an average of 68.33 grams. As for the rubric for this section, make sure we have an equation. We show our work, okay, and as long as we correctly solve it, we'll get full credit for this one. We also can have some other ways to solve this as long as there's a mathematical justification for getting this answer. It's partially correct if you have an equation set up correctly, but you make an error in applying those properties of expected values, or poor communication of the procedure. One other note down here, if you skip subtracting that 20 and jump right to 820 divided by 12, that's an example of poor communication. Make sure you show all your work, no matter how inconsequential the step seems. Section 2 is where it gets a little tricky. It's saying what's the standard deviation for the weight of these eggs. We know the standard deviation of the total container is going to be the sum of all the variances of the individual parts. Inside this container, we have the weight of the empty container and 12 individual eggs. So we're going to square the standard deviation of that empty container, the standard deviation of the eggs squared for all 12 eggs. We don't know what that is. We have x squared 12 times. And we can just simplify that. So 1.7 is from this up here. 12 times x squared, that's what we're looking for. And then the last thing that we can fill in here is that we know what this is going to equal. This is going to total our standard deviation for the entire container, which is 7.9. So this gives us our equation. Now, if you've gotten this far, you'll probably get the question correct, although the hardest part is really coming up with this equation because you have to understand how we combine variances. The standard deviation of the entire carton is the square root of the sum of all those individual variances. Once you have that, it's just an algebra equation. Square to get rid of that square root there. Move that 1.7 squared to the other side by subtraction. Divide by 12. And square root. And we get a standard deviation of 2.27 for each individual egg. As for the grading, it's looking for these three components. Note that here it says subtracts variance. Nothing's changed. We still always add variances. We're adding all the variances and square rooting them. The reason it says it subtracts is because we know what the standard deviation of the entire carton is, and we're looking for a piece of that total, which means we have to subtract everything to the other side. If you have all three of these things, subtracting variances, using 12 correctly, and finding the correct standard deviation, you get an E. If you have some kind of response where you're combining variances and include 2 out of these 3 components, you would get a P. Now that wasn't an easy question, especially the third part. The average on that question for everyone who took the exam was a 1.61. Obviously you can't get a 1.61, you'll get an integer value between 0 and 4. To get a 1, you need one section correct, the other 2 sections incorrect in any combination, or you need 2 partially corrects. Okay, that gets you at least some points, but you're still below average. If you increase it to the next score, you're now above average. And it's really not that difficult to do. That first section, that first question was just a z-score problem. We can all get that section right. Now we just need one other p, and that bumps us up to a 2. Okay, all these are 2s, EEI, EPI, 3 Ps, or an E and 2 Ps. So if you had the first section right and get just enough in that section right to get a partial credit, you're now at a 2, you're above average. 3 would be an E and a P. Obviously in any combination, that P can be anywhere, not just the third section. And for 4, you need 3 Es.